Hello everyone, welcome to my third lecture of quantum mechanics. In the previous lecture, I talked about mainly inner product and inner product spaces, and this lecture will be about mainly introduction to operators. Let's start today's lecture from the first topic we will learn today is something called subspaces. So I will first give the definition. The definition of subspaces is given a vector space V, let's say a subset of its elements that form a vector space is called a subspace. We will denote a particular subspace I of dimensionality Ni by Ni. So we'll call a vector space, we'll take some elements of a vector space, and if those elements together form a vector space, we'll call those elements a subset of the original vector space. It will be clear if we give some examples. Right, first one is, let's say, all vectors along the x-axis. All vectors along the x-axis, let's denote it by this. So this is a subspace of two-dimensional xy vector space, right? Because all the vectors along the x-axis also follow the rules of vector spaces. Similarly, all vectors along the y-axis, they also form a vector subspace. Okay. Another example could be all vectors in the xy plane, the space all the vector space are subspaces of our three-dimensional vector space. So this is the definition of vector space and example of some of the vector spaces, subspaces. What will be a counter example, right? What kind of set does not follow the rules of subspace? Let's say we take the set of vectors, set of all the vectors along the positive x-axis. they does not form a vector space as the vectors in this set does not have its inverse vectors to fulfill the axioms of vector space. So if we have vector I cap, we don't have another vector minus I cap, so that I cap minus I cap can be equal to 0 vector. As this set does not follow the axiom of a vector space, it will be not a vector subspace. Another definition, and definition number 12. Given two subspaces, let's say we have two subspaces denoted by this, where they have ni and nj dimension. We define their sum will be writing like this: sum of these two vector subspaces. This sum contains, we'll say this sum contains 1 all elements of Vi subspace, 2 all elements of, and 3 all possible linear combinations of Vi, Ni and Vz, Mz. So this is the definition of sum of two vector subspaces. So example, if we only take the sum of, let's say, all the vectors along the x-axis and all the vectors along the y-axis, we will only get vectors in the xy plane but not in the direction of x-axis and y-axis. So by including all linear combination, we would get the whole vector space of xy plane. That's why we are defining the vector sum in this way. Let's do a problem now. Let's do a problem of vector space in a space. Let's denote it like this. Prove that the set of all vectors that's the v1, the set of all perpendicular vectors or orthogonal vectors to any v vector not equal to 0 form a subspace n minus 1. So we have to prove that orthogonal vectors of any vector, they form a subspace. So how will we prove that? From Gram-Schmidt theorem, we know that we can find n minus 1 orthogonal vectors to any vectors. So if we take linear combination of all those vectors, if we take linear combination all vectors orthogonal to V, we get something like this: A1 plus A2 and so on, finally AN. Okay, and we can easily denote it like this with a summation sign: V orthogonal I cap. Let's say this is equal to our V vector. Now if I take a inner product with V here, right, as they are orthogonal to V, we will find out it is 0, and from right side we will find the norm square of the vector. So which is not possible as in the problem that V is not equal to 0. So the set of orthogonal vectors does not contain V. So the space is n-1 dimensional. So as we cannot express a vector with linear combination of all orthogonal vectors, we can show that the orthogonal vectors to any vector form a subspace of n-1 dimension. So this was our content in subspace. So and now we will start a very important topic in the huge important topic for quantum mechanics called linear operators. So first we have to define what is a linear operator. So an operator, let's write it denoted by omega, is an introduction for transforming any given vector, let's say V, into another V prime vector. The action of the operator is represented as follows. omega v will turn. So any operation that transform a vector into another vector is called an operator, and we will write it like this. So this line means my omega operator acting on v vector turns it into another vector v prime. And for this course, we will restrict our attention throughout the whole course to operators omega that do not take us out of the vector space. That means v and v vector and v prime vectors are the same, not same, present in, both are present, both are not present, we can say both are elements of same vector space. So we will not talk about the operator that take a vector and transform it into another vector that is a element of a different vector space. In our content, in our course, we will only talk about the operators that transform the vectors in the same vector space. So if the operators can act on ket vector, they can obviously act on bra vectors, right? So the bra vectors, we will write them like this. Okay. So we will only focus on linear operators. So what are linear operators? Linear operators follow the rules what rules they follow. Number one rule is this. Number two, if we have any linear combination, we can write this is for ket, and what will be the representation in bra vectors. So these are the properties of a linear operator. And why do we need linear operator? It will be clear after some time in this lecture. Let's give some examples of linear operators or operators. One single, this is an operator. It takes any vector and transform it into itself. This is called identity operator. An identity operator act on a bra vector like this, we get the same vector. Some example, this operator denoted by r1 pi by 2 I cap act on the unit vector 1 so this vector rotate any vector pi by 2 counterclockwise about the unit vector I cap. So these are the some examples of operators. So why do we want to learn about only linear operators? What is the purpose behind this? So now we'll see that a nice feature of linear operator is that once their action on the basis vector is known, their action on any vector in the space is determined. What does it mean? Let's say we have a operator omega and we know what action or what transformation of I vectors does omega do. Let's say it's become I cap, I prime. So now if we know this and we want to know what does my omega does act on V. So if we want to know that, we can write V as the linear expansion in terms of basis vectors like this. There will be a summation and we can like is the linear operator. If you remember, the linear operators has this rule or follow this rule. So we'll get VI I cap. So easily, if we know what is the action on the basis vector, we can easily find what is the action on any vector for a linear operator. That's why we're interested in linear operators. Let's say, and what is an example will be of this example. Let's say we have a vector in a 3 dimension represented by this. If my operator omega is the rotation vector, counterclockwise rotation vector about the unit vector I cap, so RV can be written like this, and from the example here we all know what does 1, 2 and 3 means. So it will be 1, it will be 3, and this will be V3 2. So if we know what does our omega transform basis vectors, we can easily find what action will do on any vector V. Next, what does so now we know this, what does a operator means. Now what does the product of operators means? Like if we have omega and we have lambda, what does it mean? So the product of operators stand for the instruction, stands for the instructions that the instructions stands for the instruction that the instructions corresponding to the two operators be carried out in sequence. Okay, so what does it mean? It just means if we have this product of two operators, omega and lambda, we'll first do the operations of omega, then we'll do the operation of lambda. Okay, and here it is the ket obtained by the action of omega on our ket V. And if we have operators in this fashion, it is written like this. This is called a commutator of omega and lambda. So remember this thing, it will be helpful for us in later part of the course. So this is called a commutator of omega and lambda. So what operators are we working on first? This is very important. So we have to remember order is very important for operator. Okay. We can also define the inverse of an operator. So how will you define it? The inverse of omega denoted by omega inverse. What does it mean? Satisfies this product. So if we have an inverse of phi, it will the product of inverse of an operator with itself will give us always identity operator. So this is the definition of inverse of an operator. And what will be the inverse of the product of an operator? Product of two operators. Let me write it first. The inverse of a product of operators is the product of the inverse in reverse. So what does it mean? So if we have an product like this and we want to know what is the inverse of this whole operation, as a the operation will be this. So how can we prove this? Let's say it must be equal to I. So we have to prove this in this is equal to I. So we'll prove this. So let's write this in this way, following from the upper realization. So this product will give us I. As we know, I is an identity operator, so it does not change anything. So this will give us I. So if we don't have this, we cannot prove this. That's why the inverse of a product of operators is the product of the inverse in reverse. So the next, this is our introduction to linear operator, and in the previous lecture that we showed that we can express our bra vectors and ket vectors in matrix form. So our next target is to show what will be the matrix form of linear operators. So our target, our next topic is matrix elements of linear operators. Let's say we have an operator that acts on a basis vector and give us I prime. So we can write now. If we take the inner product of j and I, we'll get j and I prime. We'll get j like this. So we'll find an object like this. This, and it will have n square numbers, right? For all the j and for all the I, it will have n square numbers. So the n square numbers del ij or ji, we can denote it, are the matrix elements of omega in the basis I. So let's say these are the if we write this, in this form, we got j, vj, I, phi j. So we can represent the matrix element like this. So what will be the representation of this in matrix form? So the above equation can be presented in matrix form. Like this. And here it will be 2 omega 1. So this is the matrix form we are talking about. I J. So we can also represent the operators in matrix form. It will be much clearer if we do a problem. So problem will be, what is the matrix that represents our rotation matrix around about the I unit vector in the 1, 2 and 3 basis. What will be the form of this operator matrix in matrix form in this basis? So let's solve this. So we know these are the matrix element. So if we want to write it in matrix form, 1 R 1, 1 R 2, and this is the so this is the whole matrix of rotation vector, and we know the operators of rotation matrix on rotation operator on the unit vector like this. So if we apply this, we'll find out that this one will be 1 inner product with 1. This one will be 1 inner product with 3. The third one will be minus 1 inner product with 2. 2 inner product with 1. 2 inner product with 3, 2 inner product with -2, 3 inner product with 1, 3 with 3, and 3 with -2. So this is one, we know for our 3, this is Kronecker delta for orthogonal, so we can find this will be just this. So this is the metric representation of our rotation vector R around the y-axis, x-axis. So this is how we can find the matrix element of any linear operator in a certain basis. We'll do another problem. The first problem was we determine the matrix elements from the operator. Now, from the action of the operator, now we are given a matrix and we'll try to find out what is its action. So we are given a matrix like this. So our problem is, what is its action? So from the formula for matrix element, we can easily find from the upper that this is given 1, this is given 1, and this is 1. So what does it mean from the first one? So this means if we apply our omega on 3, it will give us 1. If we apply omega on 2, it will give us get 2. If we apply omega 2, it will give us 3. We are sure of this. So what is the action? So notice this is given 2. 1 can be written like this also. So we can write omega 3 equal to 2. And again this 3, omega 3 can be written like this. So we can write omega 2 is equal to the get vector 2. So we are sure that the product of continuous 3 omega operator gives us linear operator. So what does it mean? So it means that if we apply the linear operator omega 3 times, the vector does not change. So we can interpret this action, the action of is equivalent to rotation of the coordinates coordinate axis along 111 by 120 degree. So if we apply it 3 times consequently, the rotation will be 360 degree, which will be which will give us the identity operator. So if we want to find out what is the matrix form of the identity operator, we'll find this. How will we find this? Obviously, I identity j will denote it like capital IJ, and this does not change, so I j, it gives us just Kronecker delta. So thus I is represented by identity matrix. Thus I is represented by a diagonal matrix with ones along the diagonal, which we know is called identity matrix 1 0 0 0 1 0 0 0 1. So identity operator is represented by identity matrix. The next topic is called the projection operators. So obviously from the name we can easily figure out that the operator will give us the projection of any vectors along any certain way. Let's see how to find such kind of operators. Any vector, kth vector v, can be written like this, where I are the orthonormal bases. Obviously we can write our vi like this. So this can be represented like this, 1 to n. So what does it mean? What does it mean that this whole thing as a just represent our I. So I, the identity operator, can be written like this. First we have to take the bra vector, then the kth vector. Okay. This relation is a special relation. It has a name. It is called completeness. Completeness relationship. And this object without the summation, is denoted by pi, is called the projection operator. It's called the projection operator. Why is it called the projection operator? Let's see what are the action of pi is. So if we write this, it gives us VII. So since PI projects out the component of any ket V, right? If we take the V and projection operator tells us what are the components of ket vector V in along the direction I cap, this is called a projection operator. So obviously projection operator has also act on bra vector. Let's see this. So from bra vector we can see this is just complex conjugate of the components. And if we take the product of two projection vector, different projection vector, we will find that this is given by this. This is del ij, Kronecker delta, and this whole thing can be written as del ij pj, right? So what does this relation tells us? This relation tells us that once Pi projects out the part of ket vector V along I, further application of Pi make no difference, and subsequent application of Pj where j is not equal to I will result in 0, since a vector entirely along I cannot have a projection along a perpendicular direction j. So what if we want to write the projection operator in matrix form? How will it see, right? How will it look? Let's say 1, let's 0. The sum will, the matrix operation will look like this. So it will give us a matrix 0 and also 0, 0, just a 1 in a particular direction depending on I. This product like this product we have write this product, this is different from inner product notation, right? So this notation here is called outer product. So inner product gives us a complex number by definition, and this gives us a matrix. Now we have seen the matrix elements of operators, linear operators. Now we want to how to represent the matrices corresponding to product of operators. So our next topic is matrices corresponding to product of operators. Let's say we want to represent the matrix elements of omega into lambda like this. By definition or by notation we know the matrix elements are like this, and if we write it like this, identity matrix identity operator does not change anything, so we can write it. So from identity, from completeness theorem, we can write I, we can definitely write this. This is the completeness relationship here. Now this thing is the elements of matrix elements of omega in the bases, and this is the so thus the matrix representing the product of operators is the product of the matrices representing the operators. So basically they are saying us that if we have operator like this, like let's say 1 0 0 0 0 1 0 0 1 like this, and another operator that is 2 0 0 3 0 4 1 0 5 6, the product of them will be the product of these two matrices. So this is the matrices corresponding to product of operators. Now the next topic, the adjoint of operator. Adjoint of operator. Let's say we know we can write ket vectors like this and bra vectors like this from previous lectures. In the same way, we will write this and the corresponding bra is so here we take the complex conjugate, and here we are taking the adjoint of omega, which defines, this is the definition of adjoint of an operator. So what does it tells us? What does it mean? It tells us that if omega turns a ket v to v prime, then the adjoint of omega turns the bra v into the v prime. So this is called the adjoint of omega. So what will be the matrix element of adjoint of omega? This is by definition given by this. So we can, from the definition, we can write like this, and from the definition of inner product, we can definitely write it in this way. So we find out, so our adjoint of ij is equal to complex conjugate of Ji. So in matrix representation, adjoint of omega is the transpose conjugate of the matrix representing phi. So let me write this. The matrix representing adjoint of omega is the transpose conjugate of the matrix representing omega. The adjoint of a product is the product of the adjoint in reverse. So this. So let me prove it. Prove of this statement that this is equal to this. How can we know it is true? So if we take this, right? If we take this, we can definitely write it like this. So by the definition of adjoint operator, this is like this, or the same thing can be written like this. And again, so as both of them are equal, so this is equal to this. So finally we can conclude that if we take the adjoint of any product of operations, it will be equal to the adjoint product of the adjoints in reverse. So this is the adjoint of operators, how adjoint of operators are defined. So let's say we will conclude this. Let's say we have something like this. Indicate is given by the linear combination of some other gates in this form. Let's say it is given in this form. So the corresponding, what will be the corresponding bra of this gate? Corresponding bra will be written like this. And what will be the right side of this equation? It will be V2 bra and alpha 2 conjugate. V5 and V4 will, the order will be reversed. V3, and there will be star. So this will be the corresponding, so the order of the product will be reversed and adjoint of the operators will be applied. So these were the adjoints of operators. Our next target is to study two very important operators. We'll first just give definition 13. An operator omega is Hermitian if the adjoint of the operator is the same as the operator itself. And definition 14 is an operator omega is anti-Hermitian if the adjoint of the operator is equal to the minus of the operator. And every complex number, we know every complex number, every number can be written as alpha equal to alpha plus, right? This every complex number can be written like this. Similarly, for operators, every operators can be written like this. So if you carefully see this part, only this part, if you take the transpose of this is Hermitian, it does not change, and this part gets changed and there is a minus, this get this, and this is the transpose sign is transferred and it is minus equal to itself. So this part is anti-Hermitian. So any operator, why are we learning Hermitian, anti-Hermitian? It will come back later in later course, later lectures. So every operator can be written in Hermitian plus anti-Hermitian form. So let us do a problem related to Hermitian and anti-Hermitian. Let's say you have two operators omega and lambda, both are Hermitian. Both are Hermitian operator. So what can we say about their product? Their sum of the products in this form, they are commutators and commutator with complex number I multiplied. So are these four Hermitian or anti-Hermitian or nothing? We'll see that. So solution. So let's see the first one, the product of the, if we take the adjoint operation by definition of adjoint operator, this is like this. So if both of them are Hermitian, that means this is equal to lambda and omega, or adjoint of omega is equal to omega. So this is, so obviously this is not equal to this. So not Hermitian and not anti-Hermitian. Okay. And the second one, what about this? So obviously there is a plus sign, so we can write it like this. And the order will change, as we know. This is Hermitian, this is Hermitian, so this and this. The order of the summation does not matter, so we can write it like this. So definitely this is Hermitian. And the commutator, right? The commutator is given definition is given, the definition of commutator. So this is Hermitian, it will not change, it will not change, it will not change. So we did not find the original thing, but as you can see, if we take a minus common, if we take -1 common, we'll see this is like this. So this is anti-Hermitian. Now we just have one left. So we know the adjoint is on the complex number I, is just -I, complex conjugate, and the inside it will be like this. So this is, order will change, and this will like this. As they are Hermitian, so the adjoint of these operators are equal to them. -I. If we take a minus common, if we take -1 from them, we'll find they form like this. This minus and minus gives us I. So it is the same equal of the initial n, then this is also Hermitian. This was the definition and some examples of Hermitian operator and anti-Hermitian operator. Another important operator, definition 15. An operator called unitary operator. Let us define it first. An operator U is unitary if U into its adjoint is given, give the identity operator. That is, the adjoint of U is equal to the inverse of U. So this is the unitary operator. Again, why it is important, it will come in the later part of the courses. So let's do a problem from this definition. Show that a product of unitary operators is unitary. So if we take two operators and two unitary operators and take product of them, the result will also be unitary. We have to show them. So for proof, let takes this product. By the definition of product of operators, this is this. As Vn, let takes U and V unitary. So if they are unitary, V into V adjoint is give an I, and U prime also will give I. So obviously if they give us I, so this is unitary. Theorem 7. This is very important theorem. Unitary operators preserve their inner product. Between the vectors they act on. Unitary operators preserve the inner product between the vectors they worked on. What does it mean? Let's see. Proof. So let's say unitary operator does this operation. We get v1 prime from v1, v2 prime by acting unitary operator u on v2. Now if we take the inner product of v2 prime and v1 prime, we can definitely write it from inner product rules. This is, as u is a unitary operator, so this will give us I. So v2 into I and v get, right? So I doesn't change anything, so v2 inner product with v1 is. So if we apply unitary product, the inner product will always be same, it will not change. So what is the physical meaning of this? If we consider the rotation vector in 3 dimension or 2 dimension, when we rotate a vector, we only rotate a vector, we does not change the length of the vector. And when we take dot product, as the length and the angle does not change between the vector, the dot product is always same, no matter how many rotation we do. Also we can see from here that unitary operator preserve the inner product. So we can connect these two. So we can say unitary operators are generalizations of rotation operators from three-dimensional to n-dimensional complex plane as rotation preserve the length. Okay, this was theorem 7, and what is the intuition behind it, and theorem 8. Theorem 8 tells us if one treats the columns of an I have to write this, it is a very big theorem. If one treats the columns of an n into n unitary matrix as components of n vectors, these vectors are orthonormal in the same way the rows may be interpreted as components of an orthonormal vectors. So we have to prove this. So this is telling us that the matrix element of n into n unitary matrix, all the column can be treated as an vectors orthonormal. So we have to see this. What is the proof of this? From the definition of unitary matrix, we know this, and from the element of identity matrix, identity operators, we know this. So we can write from I to unitary this. So from completeness theorem, we can easily write summation of k is like this. You can write it, nothing changes. So this one is the vector matrix element of this vector, and this is the matrix element of this vector. So they are equal to del ij. So it proves our point that if we take product of the unitary matrix and its adjoint, it gives us the identity matrix. So we can say that column of an n into n as components of n vectors. In the same way, the rows may be interpreted as components of an orthonormal vectors. So this will be our so we'll now see a problem, and this will be our last problem. Prove that the determinant of a unitary matrix is a complex number of unit modulus. So we have to prove that the determinant of a unitary matrix, or I hope we all know what is the determinant of a matrix is. So let us prove this. So we know this determinant of identity matrix is always 1. This is the property of identity matrix, and we can also write like this. We know the transpose of an unitary we know this from matrix relationship, that the product of matrix, the product of the determinant of the product of the two matrices are equal to the determinant of the product of the individual determinants of those matrices. So from transpose formula we can write this. This is transpose. So we know the what does the adjoint mean. We need to take the transpose of the matrix and then complex conjugate of the numbers. So determinant of transpose of a matrix and the matrix is same. So definitely we can write this. So what does it? It will give us determinant square from the properties of a complex number. We can say this. So determinant of square is now equal to 1. So what does it tell us? It tells us that so determinant of my unitary matrix is a complex number of unit modulus. Okay, this is where I will end this lecture. If I am wrong in my explanation in anywhere, please do comment. Thank you.